The end behavior of the polynomial function is what the function looks like as the value of x increases. So as x increases, the function is going toward positive infinity, so it is open upward. And that happens because the degree is even and the leading coefficient is positive. So in this case, the leading coefficient is 1. So it is open up and it rises in the right-hand side and rises in the left-hand side toward infinity. If the degree of the polynomial is even and the leading coefficient is negative, then the function is going to fall on the right-hand side and it is going to fall on the left-hand side also. So if we draw a straight line, it is going toward negative infinity on either side. So it's going or falling on the left-hand side and it's falling on the right-hand side. If the degree is odd and positive, then the function is going to rise on the right-hand side, which is over there, and fall on the left-hand side. So it is going to go toward positive infinity and it is going to go toward negative infinity on the left-hand side. If the degree is odd, but the leading coefficient is negative, things would just flip. So we would have the function going to the negative side on the right and rising to positive infinity on the left-hand side. So we want to use this leading coefficient test to determine the end behavior of the graph of the following functions. So here the leading term is x raised 4, which would imply a degree of 4, which obviously is even, and the leading coefficient is positive. So we could go back up here. So even degree and leading coefficient is positive. The end behavior is rise, rise, and rise left. So this problem is kind of tricky, the one in part B. So when you look at the polynomial, if you FOIL this, you would actually end up getting a regular polynomial. So I'm just going to show you, but technically it is not needed in a problem like this. So 2x cubed, if we FOIL x minus 1 and x plus 5, we have x squared plus 4x minus 5. Distribute the terms, or distribute 2x cubed. You would have 2x raised 5 plus 8x raised 4 minus 10x cubed. And naturally, the leading term is 2x raised 5. The leading coefficient is 2. The degree is 5. So what we have here is an odd degree and a positive leading coefficient, so the curve has to rise on the right hand side and fall on the left hand side. So So a key thing to notice here is that the foiling and distributing of the 2x cubed inside the FOIL part is unnecessary. So all we have to do to determine the degree is to simply multiply the leading terms in each of those factors. So what we have is 2x cubed times x, and that would give us 2x raised 5, and you can see that the leading term is 2x raised 5. Mind you, this trick only works if you have every single factor, for instance 2x cubed, x minus 1 and x plus 5 written in the proper form. In other words, the highest power has to be the leading term, and subsequent terms have to follow, or subsequent powers, decreasing powers, they have to follow the leading term. So moving on to C, the leading term is negative 0.27 x cubed. The degree is 3. The leading coefficient is negative 0.27. So the leading coefficient is negative, it's a negative value, and the degree is odd, so the end behaviour is rise on the left and fall on the right. The zeros of the polynomial function are simply the roots of the polynomial, which are simply the x-intercepts of the function, which is the same as the points where the function crosses the x-axis. So to find the zeros of the function, we are pretty much finding the x-intercept. So as the standard rule of thumb, you set the function equal to 0 and you solve for x, and that is going to give us all the zeros. Some zeros can occur multiple times, so such as you have x minus 1 raised 3. So there is 1 0, so the entire function would become 0 if you plug in 1 for x. So that 1 0 is x is equal to 1, but it repeats itself 3 times. So pretty much it's over here. I'll fill in here. So x is 1 is the only 0, and it occurs, technically speaking, it repeats itself 3 times. So if a 0 repeats itself, the number of times it repeats is called the multiplicity of the 0. So in our example, the 0x is equal to 1 repeats 3 times, so the multiplicity is 3. In general, a function of that sort would become 0 if x is equal to r. So plug in r for x, r minus r is 0. So x is equal to r is a 0 with multiplicity k, because we are looking at that value over there. So multiplicity is k. There are a few things that multiplicity can tell us. So if we have an odd multiplicity of a 0, then the function is going to cross the x-axis. If a 0 has an even multiplicity, then it is going to touch the x-axis and it would make a turn. So consider y equals x plus 3, which is a straight line. I could write it as x plus 3 raised 1. And 1 is an odd number, and it just repeats ones. So the multiplicity is 1, it is an odd number, so you can see that the function crosses the x-axis. But on the other hand, if you look at y equals x minus 3 squared, 2 is an even number, and this curve belongs to that, that function belongs to that curve, which is the parabola. And you can notice right here, it touches the x-axis and turns around. So if we continue this for any polynomial, here we have the multiplicity to be 3. The 0 is 3, because if I plug in 3 for x, 3 minus 3 is 0. The function becomes 0. So that is the 0 of the function. The multiplicity is odd, therefore it is going to cross the x-axis, and it is crossing at the 0, which is x equals 3. So over here, when x is equal to 3, that function would become 0, because 3 minus 3 is 0. The multiplicity here is 4, which is even. So the function, that red dot, is actually x is equal to 3. So it is the 0. The function is coming down, touches the 0, and turns around in the other direction. In the next function, we have degree of 5. Polynomial has degree 5. The multiplicity is 5, and the 0 is simply 3. Again, 3 minus 3 would be 0, so the function becomes 0 at x is equal to 3. Therefore, that is a 0. So here, the point where it crosses the x-axis is the 0 of the function. And in this graph, it crosses the x-axis because the multiplicity is 5, which is an odd number. So anytime you have a function such as this, you have two factors. So that is one of them, so I can set x plus 3 equals 0. And over here, I have x minus 3 equals 0. Setting the function equal to 0, I'm solving for x. So x here is negative 3, and x there is positive 3. This particular root, or 0, has a multiplicity of 3, because it repeats 3 times right here. And that one has a multiplicity of 1. In the graph, that point is x equals 1, and that point, x equals positive 3, and that point is x equals negative 3. Both of the multiplicities are odd, and we know that if a root or a 0 has odd multiplicity, the function is going to cross the axis. So it crosses at x is equal to minus 3, and it crosses at x is equal to positive 3. In the next function, we have x plus 2 equals 0, and x minus 3 equals 0. So x would be minus 2, and x would be 3 there. And you can see that if I plug in negative 2 in x plus 2 raised to the power of 3, the entire function is going to become 0. Likewise, if I plug in 3 for x in the second part, which is x minus 3 squared, 3 minus 3 is 0, the entire function is going to become 0. So you can see at x is equal to minus 2 right here, and x is equal to 3 there, the function has a 0, which is why we have red dots on the x-axis. But the degree of, the multiplicity of 0x is equal to minus 2 is odd. Therefore, it is going to cross, the function is going to cross the x-axis. So it is a crossing. But on the other hand, the root x is equal to 3 has an even multiplicity, so the function is going to touch and turn around. So you could learn a lot of things about a polynomial just by observing its degree, the multiplicity of the roots, and so forth. So in this function, we have two factors. So I could set each factor, so that is factor 1, and that is factor 2. So all we have to do is set each factor equal to 0. I'm setting x minus 3 equals 0, which would imply x is 3. And the second case, x minus 1 is equal to 0, which would imply x is equal to 1. And we therefore have the zeros of the polynomial, which are 3 and 1. So the function would behave depending on the multiplicity of each of those zeros. You can see the multiplicity of x is equal to 1 is odd. So, or x is equal to 3 is odd. So the multiplicity of 3 which is odd. The multiplicity of 1, which is right there, is 2, and it is even. What do we know? If the multiplicity is odd, then the function is going to cross the axis. If it is even, it's going to touch and turn around. So, function crosses the x-axis at x is equal to 3. Over there, the function touches and turns at x is equal to 2. Oh, sorry. 1. So, if you look at the previous problem and the ones before, we have it nicely factored. So we have x plus 3, x minus 3 whole cubed, and so forth. If you have things factored, then we can find the zeros easily. But you look at the current problem, which is part B, it seems as though the problem is going to be difficult, but it is designed in such a way that we can easily factor. So if you look at the first two terms, we have x squared in common. So if I pull x squared out of x cubed, I will get x. If I pull x squared out of 5x squared, I will get 5. Likewise, if I pull a negative 9 out of the last two terms, negative 9 comes out of 9x, or negative 9x, we have x. Negative 9 comes out of negative 45, we have plus 5. Now, the x plus 5 is common in the first and the second term. So we could pull x plus 5 out. So when it comes out of the first term, it leaves behind x squared. When it comes out of the second term, it leaves behind 9. But if you recall one of the identities of algebra or quadratic functions, x squared minus 9, I could write it as x plus 3 times x minus 3. If you FOIL that part, it is going to result in x squared minus 9. So we have 3 zeros. So x plus 5 equals 0, which would imply x is negative 5. X plus 3 equals 0, which would imply x is negative 3. X minus 3 equals 0, which would imply x is equal to positive 3. And all of them have a multiplicity of 1, and it's odd. So what do we know about odd multiplicity? The function is going to cross the x-axis at x is equal, or at each of those zeros or roots of the polynomial. So the function crosses the x-axis at x is equal to -5, x is equal to -3, and x is equal to +3. The next one is the intermediate value theorem. People get scared if we use the word theorem, but this is actually a very, very simple theorem. So if you pick two numbers, a and b, which would form an interval, so x is equal to a, x is equal to b, and if the function changes from negative to positive or positive to negative, for instance, right over here, the function is negative, and right over there, the function is positive. So clearly the sign changes, so there has to be a zero crossing somewhere in the middle. That's why we call it the intermediate value theorem. In between a and b, there has to be a zero crossing, or the function has to cross the x-axis if the sign changes on an interval between a and b. So the key thing to notice here is the problem has to specify the interval, or else you'd be searching aimlessly. So as an example, consider number 4. The function is 3x cubed minus 10x plus 9, and we want to know if it has a 0 between -3 and -2. So that would be the value of a, and that is the value of b, and -3 all the way up to -2 is our interval. So all we have to do is plug in -3. So we have 3 times -3 cubed minus 10 times -3 plus 9. So 3 times -27 plus 30 plus 9. So -81 plus 30 plus 9. And we have -51 plus 9, which is -42. Clearly, it is a negative number. Now I'm going to plug in the other value, which is -2. So 3 times -2 cubed minus 10 times -2 plus 9. So 3 times -8 plus 20 plus 9, which is -24 plus 29 equals +5. So as we move from -3 to -2, which is our interval, the function moves from -42 to +5. In other words, there is a sign change in the function. Since there is a sign change in the function, there has to be a real zero between those two values. And that's exactly what the intermediate value theorem states. So in this problem, it's given that x is equal to -1 and x is equal to 0 would form the interval. So that is A and that is B. So we take the values and plug it in for the function. We start with A. F of -1 would equal 2 times -1 raised 4 minus 4 times -1 squared plus 1, which is 2 times 1 minus 4 times 1 plus 1. 2 minus 4 plus 1, which is -1. And when we plug in f of 0, we have 2 times 0 raised 4 minus 4 times 0 squared plus 1. So 2 times 0 is 0, same here, 0 plus 1, we have 1. So as we move from -1 to 1, the function moves from -1 to +1. So this would imply there is a sign change between x is equal to -1 and x is equal to 0, which would imply that there has to be a real 0 between x is equal to -1 and x is equal to 0.